Okay, thanks, Arvind. So first I'd like to thank the organizers for inviting me to Bangalore ICTS. It's fantastic to be here. It's a fantastic place. Okay, so I'm going to be talking about some work that's joint with Fabio Toninelli, who's based in Lyon. Okay, so the setting that we've got is that we're considering a stochastic growth model modeled by some Markov chain with some local rule. So typically, the models I'm interested in are 2 dimensions, and it's got like some kind of surface type of growth. There are many different questions that you can ask on these types of models. For instance, you can ask for the stationary states. Run your dynamics. Have you got a stationary state? You could look at the space-time correlations of your height function. So you look at your surface, look at a particular point in your surface, and see what the how it correlates in space and time with other particles. You can also look at the hydrodynamic limit. As a little warm-up example, just so that it just sets the scene, we'll consider a Markov chain modeled by stacking boxes. Okay, so this Markov chain has the following. So a box you can look as a hexagon. And you can go from having an empty box to a full box. And we'll do that with rate p, and it goes backwards with rate q. Okay. So I have a small simulation of how you can do that. So let's see if it runs. Okay, so this is just in the case when q is equal to 0, so it only can grow. Okay. So you get something that forms like that. So you can, so as time goes on, you keep adding these boxes with a rate, and you can see that you get some surface that evolves in the 1, 1, 1 direction. Yeah, so I didn't tell you anything about the dynamics, and I did that on purpose. So this was a picture that I was able to draw using my rudimentary skills rather than trying to do anything complicated. So I think in this particular case, it was if you can, you look at all the possible places where you can throw a box, and then you throw a box. Okay? But the exact dynamics aren't actually necessarily important here, just for pedagogical purposes. Okay, so you could see from that picture that you get some kind of surface that evolves. And you can see that, if I go back a little bit and just pause it, you can see that, you know, at particular points, like if you let this picture get really, really large, you could zoom into particular points and look at the slope, and the slope will change as you go from one corner, like here, all the way across to there. Okay, so in this model, when P is equal to Q, you get a model that grows, just as we saw in the picture. And when P is not equal to Q, when P is not equal to Q, you get a model that grows. And when P is equal to Q, you get no growth. So it's just like some kind of stationary process. Right. So so if you go back to that video that we just had, you've got a height of the interface, and for some particular cases, just to motivate what's happening, you can look at the height between 2 different points, and this is given by the slope times the distance between the 2 points. And as we saw in the video, as your interface grows, so as you let time grow, your interface will grow. And there is a particular parameter that we're interested in, and this is called the speed of growth. So all this is that you look at a particular slope, rho, you look at your height function at time t, and you subtract your height function at time 0, and you divide by t. And this we call the speed of growth. So we're looking at this interface growing. And this will be called the speed. Okay, so one expects that if you look at large distances between x and y, that if you compute the variance between 2 points, you expect that it behaves roughly like C1 plus C2 times x minus y to the alpha, where alpha is something. And then for large times, if we look at the variance between the height that you get at time t and the height at time 0, you expect this to be of the form C3 plus C4 t to the beta, where beta we haven't given. So this top one here, this alpha here is often sometimes called the roughness exponent, and this beta here is called the growth exponent. Nikos, did you want to see the video? I'll show it to you now because I think Herbert missed it too. So I just showed them a brief video about, you've probably seen this very many times, but it's just adding boxes and you get some height profile that grows, okay? Okay, so that's kind of the setting. Okay, so if we look at fluctuations, so what one expects is that one expects to see like the height function fluctuations to be of KPZ type. Okay, so we saw the KPZ equation this morning in Tomohiro's talk. So you've got the partial derivative of h is equal to Laplacian of h plus some nonlinear term, which we stick a lambda in front for tuning purposes, and a white noise term. And here in the nonlinear term, we've got this h of rho, and h of rho is just the Hessian of the speed of growth that we had on the last slide. So it's just computed by computing second derivatives. Right, so when lambda is equal to 0, this corresponds to something called the Edwards-Wilkinson equation. And here you'll have a specific alpha and a specific beta. Okay, so different things happen in different dimensions. So the case Tomohiro was talking about was dimension equal to 1. So it was quite, so this equation here wasn't originally well posed, but now is from Hera's regularity structures. So when d is greater than or equal to 3, it's predicted that that for some parameters of this lambda, for some values of this lambda, this nonlinear term is not important. So then you just get the Edwards-Wilkinson equation. And for some parameters it is. When d is equal to 2, which is the case that we'll be looking at, there is an expected, if you replace this nonlinear term by just grad h squared, there is a particular transition or expected transition for lambda c. So I guess Karavina, Sun, and Zigouros recently posted a paper that if lambda is less than lambda c, then you get the Edwards-Wilkinson equation. Yep. Okay, so just when lambda is very, very small.
So what they prove is, I mean, both groups have somewhat different results, but you know, the general claim or general result of the proof is that if you're in dimension d greater or equal to 3, and if you take lambda sufficiently small, in fact, in their proof, I mean, the lambda presumably has to be very small, but anyway, take it sufficiently small, then if you then look at the long time behavior of the nonlinear equation, it will agree with the Edwards-Wilkinson.
Okay, so, yeah, okay. Thanks, Harold. Yeah. In dimension 2, yeah.
Okay, thank you. So also in dimension 2, you take lambda scaling to 0, but the difference with dimension 3 is that the nonlinearity is relevant in a sense, because it changes the noise.
Okay, so
it changes the strength of the noise.
Okay, so you mean that you can change this lambda into there or something?
So there is a parameter lambda going.
Yeah. Okay. Oh, thanks. Okay, so there is a conjecture by Wolf made in, I guess, the early 90s that in dimension 2, based on, if you look at the sign of the determinant of the Hessian. And the conjecture is as follows. If the determinant of your Hessian is positive, then the nonlinear term is really relevant. And if the determinant of your Hessian is less than or equal to 0, then the nonlinear term is irrelevant. And from this, there are two universality classes defined. So when it's positive, it's said to be isotropic KPZ. And when it's less than or equal to 0, it's said to be anisotropic KPZ. So for the first universality class, the isotropic one, as far as I'm aware, it's only been verified by numerics. Okay, so very little is known. In the anisotropic KPZ, a bit more is known, or quite a bit more is known. So it's known that the alpha and the beta, so the growth exponents and the roughness exponents are both 0. And you expect that the variance of the height function behaves like log t as t goes to infinity. I'm not sure on that, actually, what's the reason for the names. Yep, so this has been shown in so for the anisotropic KPZ, this log t for the variance was shown in a specific model by Prechofer and Sporn. There are other examples too, such as a random growth model that Borodin and Ferrari introduced, which we'll talk about in a second, which was generalized by Fabio Toninelli recently in 2015. So anisotropic, it's like you've got no yeah, actually I don't know how to explain them actually. Just take them as two different universality classes that you can have. Okay, so our question is actually quite simple. So our question was, this Hessian that you've got relies on V being twice differentiable, right? Because if you want to take the Hessian, you need two derivatives. So we were wondering what happens when V of rho is not twice differentiable. And the second part that we were wondering was that these models for the anisotropic KPZ class, here you've got this height function whose variance behaves like log t, right? So in terms of diamond model language, you think, well, log t is like a Gaussian free field, so you think that it corresponds to something being in the rough phase. And for these statistical mechanical models where you've got a rough phase, there are models where you get smooth phases, which have exponential decay of correlations. So we were wondering what happens when you change the correlation structure from going polynomial decay to exponential decay. And do you see anything different occurring? So that was like the main question behind our research. Okay. So, and that will be the main focus of the talk, is to introduce dynamics that allow us to actually answer, or partially answer, this question. Okay, so a little bit about some known results. So Borodin and Ferrari, they introduced a specific set of dynamics for lozenge tilings. I might just give you these. So their initial array was that they considered this triangular array of particles, which you can also view as lozenge tilings. Okay. So their initial condition was a triangular array. And these particles had to interlace. meaning that this particle has to sit between this one and that one. Okay? So I can't have this particle being outside further across than this particle. So this particle with my right hand needs to be to the left or at the same position as this particle, and this particle here needs to be to the right of this particle here. Okay. Yep, and they're all going to be traveling to the right. Okay. Okay. So each particle can jump, if it can, with probability, like with rate 1 to the right, and when it jumps, it takes the whole block. Okay. So for instance, if we allow this particle here to jump, it will also pull these particles all the way across. So for instance, if we allow this one to jump, so this second particle jumps to the right one step, okay, it takes the whole column with it. And I've got one. This is the column, right? It's the column, okay, but it only takes the column above, okay? So if you look at this configuration here, which I'll draw in green, say, this configuration has now moved to the right one step. And in order to satisfy the interlacing constraint, this particle always needs to sit to the left of this one. So if this one wants to jump, it's blocked by this particle here. So this particle here is blocked by that. Strictly, so if you want some notation, if this particle is x1, 1, this one is x2, 1, x2, 2, I need x2, 2 to be less than x1, 1, which is less than or equal to x1, 2. Okay? And the same for all levels going upwards. Okay, so Borodin and Ferrari, they introduced these dynamics, and the way that you can view this as a lozenge tiling model is that everywhere we see a particle, it's equivalent to just having a particle on these lozenges that are of this type. Okay? So you can replace your picture by this, where you have a lozenge of this type, and where you have particles just corresponds to lozenges of those types. You might have to rotate the picture slightly for this to work. Okay, so one of the things they were able to do was that they were able to compute the speed of growth for this particular model, and they found that it had a quite nice formula. And this formula is given by V rho 1, rho 2 is given by a rational function involving sines of the slopes. Okay, another thing that they found was that if they looked at the height function and they minused by the expected height at that particular point, then the fluctuations of it are size square root log L. And they were also able to show that as they had this specific formula of the speed, they could show that it belongs to this anisotropic KPZ class. Right, so later, 7 years later, Toninelli introduced some dynamics that were based off this model, but now held for the plane, and allowed you to jump backwards as well as forwards. So you're allowed to jump backwards and forwards. So, and he showed that these dynamics were actually well-defined and stationary. So the problem with these dynamics is that when you do move one particle, like to the right, you can end up moving a whole infinite string of particles going up. So you need to, so the dynamics aren't local, so you need to check that they're actually well-defined. So it's still Z2, but here you've got here you've got an initial condition, right? So I'm just thinking of think of a stationary lozenge tiling. So it's got the same measure everywhere. So his dynamics work just, for the whole plane where it's stationary everywhere. Does that make sense? So take a lozenge tiling. So you can take a lozenge tiling on the torus, for example, and then let the torus get really, really large. Okay? So then you've got a lozenge tiling that has a particular slope everywhere, right? Okay, so his dynamics work for that particular case. So here, this model, exactly. Everybody can move to the right and to the left. They don't move vertically. Yeah. Okay, so Fabio wasn't able to compute the speed for this particular model, but there was a small, we did a small work with Patrick Ferrari and we found the speed for this particular model. And it turns out that it was the same formula that they got for, that Borodin and Ferrari got for their model. Okay, and just to mention, a couple of things was, for these particular dynamics, there is a hydrodynamic limit, and that was done by Laszlo and Tonelli. Okay, good. Okay, so let me introduce the dynamics that we'll be working with. Okay, so in order to introduce you these dynamics, I need to look at dimers on Z2. So I presume not everybody is familiar with the dimer model on Z2. So let's just do a brief review. Okay, so a dimer is just an edge. Okay? And a dimer covering is a subset of edges so that each vertex is incident to exactly one edge. So here is an example. So here are the vertices. You can just about make out that they're colored black and white. Okay? And you can see that these long black lines, thick lines, these are the dimers. So this would be an example of a dimer covering of Z2. You can thicken out your dimers and make them dominoes. So you can replace your dimers by dominoes, and you get a domino tiling. So these two things are equivalent. So dimers and dominoes are equivalent. Okay, you can assign edge weights. So these are just positive numbers to your edges. And then the dimer model is just the probability measure, where you pick each configuration with probability proportional to the product of the edge weights. So you just have the product of your edge weights of that configuration, and then you take the probability of picking M to be proportional to the product of the edge weights. And here, as in Tomohiro's talk, Z is just a partition function. Okay, there's, as you saw for the lozenge tiling model, that we could look at a stack of boxes as being the height of some surface. There is an idea which generalizes, and this is normally attributed to Thurston, that you have a surface representation of your dimer model on Z2. And the rule is that the heights are defined on the faces of your graph, and if you see a dimer between the shared edge between two faces, you go up or down by plus or minus 3, and if there is no dimer covering the shared edge, then you go up or down by minus or plus 1. Okay? So just, so if you've got two faces, let's say the height here is 0, and let's say that there is a dimer covering that shared edge. So here, we're going to go up by 3. We're going to set the convention so that if we go from this face to this face, and there is a green dimer, a green vertex here to the left, then this is going to be plus 3. And the opposite holds. So if we go from one face to another face, and the white vertex is to our left, we'll go down by 3. And then for the other faces where we don't have dimers covering the shared edges, these go up 1, these go up or down by 1 or -1. And the convention will be that if we go from one face to another face and the shared edge has the right vertex being green, then we'll go up 1. So we'll go up 1 there, we'll go up 1 there, and then we go up 1 there, so 3. And then if we go the opposite way, it goes down. And as you can see, it's consistent. So if you go around each vertex, it's a consistent rule. So I go up 1, 2, 3, and then down by 3. And then here would be 2 and 1. So it's divergence-free around each vertex. And one of the nice things about this height function is that there is a one-to-one correspondence between dimer configurations and height levels. So if I give you a dimer configuration, you can construct the height function. And if you give me a height function, I can construct the dimer configuration. Okay, so for dimer models on bipartite graphs, Kenyon and Kunkoff and Sheffield characterized the different types of measures that you can get for these particular models. And they found that there are three types. So it's, they called them frozen, they called them solid, or you can call them frozen. So configurations here are deterministic. There is also what's called rough, or which they called liquid, where you have polynomial decay of correlations between dominoes. And there is also a smooth phase, which they called gas, where you have exponential decay of correlations between dominoes. Okay, here, just to note that solid, liquid, and gas, these aren't physical states of matter. And just to avoid any confusion, we use the terms frozen, rough, and solid. Okay. And the measures that you get, so if you give me a dimer configuration, the measure that you'll get in the plane depends on the slope, so if you, as well as the underlying graph. So it really depends on these two things. Okay, so not all your dimer models actually give you a smooth phase, but one that does is the two-periodic weighting. So here, the weighting is as follows. So every face that's labeled A has edge weights. All the edges incident to the faces labeled A have weight A. So this edge here has weight A, this edge here has weight A, this edge here has weight A, etc. And the ones labeled 1 all have edge weights 1, 2. Okay, in order to show you some pictures about what these phases look like in the plane, it's much easier for me to actually show it to you on a picture where I can actually simulate it. And that's on the Aztec diamond. So an Aztec diamond is just a particular region. So I've rotated the lattice by 45 degrees. And an Aztec diamond, so this is an Aztec diamond of size 4. If I wanted an Aztec diamond of size 5, I'd have 5 rows of squares here, and, well, sorry, 5 columns of squares here and 5 rows here. An Aztec diamond of 6 would be, as you'd think, like 6 rows of squares, 6 rows of squares, so it would be 6 by 6. And you can assign the two-periodic weighting to this picture too. Okay, so you'd have A1, A1. So here I'm using the same convention, that all the edges around the faces marked A have weight A, and all the edges incident to the face marked 1 have weight 1. If you were to fill in the height function rule that we've got here, then the heights on the boundary faces are given as follows. So as we go up on the left-hand side boundary, it just goes up in multiples of 2. And on the bottom boundary, it just goes up in multiples of 2 as well. Okay, so now for a picture. So if you draw a picture of the Aztec diamond height function, you get a picture that looks like this. So here is one of the four corners, here is another 4 corner, and here is another 4 corner. So you can see that, or you can see that here it's flat, maybe. Okay. So let's rotate the picture a little bit. So here is the flat region, and here are the four corners. This is the frozen region, and this would be the rough region. And I'm guessing you can just about make out the gas region. So we'll just rotate it again. Okay, so now you can actually see that this really looks different qualitatively to that region. And one last rotation. Okay, so from this picture, in this particular dime model, this would correspond to the smooth phase, and here it's flat, asymptotically. And this particular part would be the rough phase, and here it's sloped. This is A is 0.5, and the size of the Aztec diamond is 800. Okay, so the dynamics that we actually introduce are based on the shuffling algorithm for domino tilings, but specialized to the torus. And they rely on two specific dimer rules. So the first one is that if we see a square in our dime model, we replace it by a spider. And a spider has four legs. So here is our spider. Okay? So it's got 4 legs and then a smaller body. Oops. Sorry. So we've got a picture that looks like we'd have a square in our original configuration, and we replace it by this gadget here. So the reason that we can do this is because let's say that just this edge was matched. So this edge had a dimer. In this configuration, we'd also want this edge to be matched. So we'd want to see something that looks like this, right? So we have a dimer here, and then we don't want a dimer going between these two. So the only configuration that we can have is that. We could simply put this dimer here instead, and then we'd have the rotation of that, etc. And we could also consider the case where you'd have 2 dimers, and then it would correspond to these 2 being matched, and then these 2 being matched. And also the configuration where there is no edges being matched here, then it would either be 2 horizontal here and 2 vertical there. Okay, so what happens to the edge weights? So if we have small a, small b, small c, small d, the edges on the legs have weight 1, and the edges are given by capital A, capital B, capital C, and capital D. So as we see from our picture here, this one has weight small d, so we need this edge here to be proportional to small d, and etc. for the rest of the weights. So it turns out that in order to get the correspondence, you need to introduce this delta, and this delta is equal to AC plus BD. And the way that you get that is just going through all configurations and just working them out. Okay, so just one thing to note is that if you take the partition function of your dime model and you do this move at one particular face, then you'll get a new partition function, and the only change is that in order to get the old partition function, you just need to multiply by delta. The other dime model move that we need is edge contraction. So if you see a case where you have one vertex and it's incident to 2 edges, then you can contract that edge, those 2 edges. So for instance, if we just go to the picture, so let's say I just see this edge, then I know that this one's going to be matched too, and so it would just correspond to that configuration there. Okay, so let's apply this the torus graph. So this is a dime model on a torus. So this is a 4x4 torus. So first we're going to assign it to, if we do a checkerboard coloring of this, we're first going to do this square move on the faces that are colored black. Okay? So we'll do it on this face, this face, this face, this face, this face, this face, that face, etc. Okay? So we're first doing it on the even faces. So if we do that, we get that. Okay? So we just applied our square move on these faces. And if we apply these square moves, we remove these black edges here, right? So let's remove them. So we get that picture there. Okay, so that's from the square move. And now we've got these vertices here, which are incident to two edges. So we can do the last thing, which is edge contraction, right? So if we do edge contraction, we get the square grid again. Okay? So that's quite good. So we've got a dynamics where we can run this on the even faces first, then do the odd faces second, then the even faces, and then the odd faces. But we now need to worry about the weights, okay? Because the weights actually could change non-trivially in doing this. Okay. The next thing that we should look at is what happens to the original dimer configuration. So if we started off with a case where we had no dimers around the square, this would change to having either this configuration or two horizontal configurations on the body of the spider. When we do the edge contraction, that squishes the legs of our spiders. Okay, so around that face, we'll be left with two horizontal dimers or two vertical dimers. If we look at the case where we have one edge around a square, then this corresponded to this position here. And if you squish the legs of the spider, then you just get the dimer on the body of the spider. And you'll notice that it looks like you just slid the dimers across by one step. So this is our sliding step. And then the last configuration is if you have two horizontal dimers or two vertical dimers. When you apply the spider move, this corresponds to having all your four legs being matched. And when you squish the legs, they disappear. So you end up with deleting all the vertices, all the edges around that face. Right, so you'll notice that these two steps are deterministic. So if I give you a configuration, they're already done. Whereas these ones actually depend on a choice. And the choice is given by your edge weights. So as I mentioned earlier, that these are the actual dynamics that James Pop wrote down for the Aztec diamond, but specialized to the torus. So we weren't the first ones to notice this. This was actually given by Kenyon and Goncharov. So they were actually interested in a much more general setting. So one of the things that happens is that it's not so nice that if I give you really general weights, that if you apply this procedure, you'll get really, really nice weights out. It turns out that there's only a few cases where you get nice weights out and they remain the same after doing this. So in particular, in the two-periodic setting, the weights actually are really nice and they repeat itself. So if you square moves over and over again, you'll get the same weight functions that appear. Moreover, they'll give you the dynamics that we want. So what happens is that on the even time steps when we apply these moves, when we have the probabilistic choice, we add two horizontal blocks. We add our horizontal blocks with probability 1/2 on vertical blocks with probability 1/2. But at odd time steps, it splits down into two parities. So of parity types 4k plus 1, and at particular points, we'll add a horizontal block, vertical block with probability a squared and 1 divided by 1 plus a squared. And at parity time 4k plus 3, we'll add it with 1 over 1 plus a squared, okay, etc. Okay, so there's the dynamics are well defined, or the dynamics are well defined with period. Right, so the nice thing about defining these for the torus is that we can then extend it to the full plane, so we'll get dynamics on the full plane. And that's what we did. So just as a summary, what we've just shown is that we can consider a growth model run by these domino tilings of the, by the shuffling algorithm. And what we mentioned earlier is that for each configuration, domino configuration that we've got a height function. So we've got a surface representation. We can run this discrete time algorithm, and so we'll get a family of height functions, H0, H1, etc. One really nice thing about these dynamics is they're local. Like we're only doing local moves here. We're not deleting columns of particles. And as I alluded to briefly, is that when you run this for the two periodic weighting, it doesn't change the weights too drastically. Okay? And you can, after even time steps, you get the same weights. So it preserves the measure. And for the two periodic model, it turns out that if you put it into the Kenyon-Akunkoff-Sheffield machinery, when you're flat, you get the smooth phase, and when you're not flat, then then your measure is rough. Okay, so we can now tell you about the two questions that we asked at the beginning of the talk. Okay, so when we're not flat, okay, so when rho is not equal to 0, we get logarithmic growth of the fluctuations of the height functions at different points. Sorry, at the same point, we look at, same, at different point, yeah. We find that the speed is twice differentiable, and that if we look at the determinant of the Hessian, it's negative. So in this picture here, we're still in anisotropic mode. But when rho is equal to 0, we get bounded fluctuations of the height function. So we're in the smooth phase. And we can show that V is not twice differentiable when rho is equal to 0. So the two questions are kind of interrelated. Okay, so the main aspects of the proof. So I'll just mention two things. So one is that the dynamics, because they're local, you can compute the speed of growth just using differences of edge probabilities. And for that, you can just plug them into Kenyon-Akunkoff and Sheffield and compute. So this means that we can get a very nice expression or a very explicit expression for V. And then we can just show directly that V is not smooth when rho is equal to 0. Okay, so just a summary is so we introduced some dynamics for the two periodic weighting and showed that non-differentiability corresponds to, in this particular case, when V is in the, when our slope is in the smooth phase. We don't know whether this is true in general, so we don't know whether this is true for general tiling models or even a more general model where we're outside the domain of tiling models. Another thing that's a bit mysterious is that we can have these general weights on Z2, and if you keep applying this shuffling algorithm, they're not periodic in the same sense in time, in the same sense like the two periodic one is. But something called the Newton polygon, which defines the phases that you can get, remains the same. So we're kind of flummoxed by what happens in this particular picture. And does this hold more generally? So does this hold for, this is for a very, very specific model. So does this hold for more general models in the KPZ class? Okay, so thank you for listening.
Questions? I have one question. I'm a bit confused actually. So, if your moves in this two periodic case are, the moves themselves are periodic, that means your height is not growing, right? I'm a little confused. Don't you want a model where the height grows linearly in time?
Yeah, so if you look at a case where you're actually in the, if you look at a case when you're in the torus, right? So you've got this, so let's say that these are like the level lines of the height function.
Okay.
Each time you run the dynamics, these are just going to slide up.
They are.
So, they're just going to, so if you fix a point, these things are always going to cross it, right? So you get some kind of,
Okay.
So you can kind of see them like going.
So even though the dimer configurations themselves become periodic, the height is growing at a
the height
linear.
is growing, yeah.
I see.
Because you can just watch them as they slide across, slide upwards.
Okay.
Good question.
So do you know what happens if you take a larger fundamental domain for the periodicity of the so you have multiple smooth faces?
It's kind of ongoing work is that we can get a formula for the speed more generally. But we can't really say so much at the moment. So we know that you can have multiple, you can have multiple smooth phases, but we can't seem to show non-differentiability just yet. So we're a bit stuck there. But we suspect that it's the same. We suspect that it's the same case here. That we suspect that you don't have you don't have differentiability of the speed. So we expect that we think that this is the same behavior that we see here will hold more generally.
Smooth phase was something like rho equal to 0. So near the smooth, I'm asking about the growth velocity. Does it have a conical singularity? At relative, around the smooth phase, or you say it's not differentiable. I'm just asking, the precise behavior.
We did work it out at some point. The way to kind of see this is that, like the dynamics, like you can look, if I just show you the two periodic picture.
Yeah.
If you look at the you can kind of, in inverted commas, look at the speed, like at this point and at this point, right? At the cusp point and at the boundary. So it's really the cusp point is the part that really really contributes to your non-differentiability.
I see.
I think it's like, when you're close, like here, it's like x to -5/2 or something for your speed.
The reason why I'm asking is, when you look at crystal shapes in thermal equilibrium, then, what you call the smooth phases, correspond exactly to having sort of singularities of the surface free energy. Now, of course, the surface free energy is sort of a different object than the growth velocity, but apparently what you are saying is that when you study the growth velocity, as soon as you sort of take your slopes in such a way that the underlying facet is, the underlying flat piece is what you call smooth, then apparently at that point, the growth velocity is non-differentiable.
Yeah, so I don't know if they're
It's a question really to everyone, yes.
Yeah, I know what you mean, but I got to give you a positive answer or a negative answer.